Ever wondered what really keeps a 400-ton aircraft safe all the way from one gate to another? Well, it's not magic, that's for sure. It's a non-negotiable playbook filled with pure mathematics, where every single calculation is designed for one thing and one thing only: your safety. When you look at a plane like this, it's more than just a machine. It's an absolute marvel of engineering, operating right at the edge of what's possible. And to make this happen safely every single time requires an incredible feat of calculation. Today, we're going to open up that very playbook for the sky. Okay, first up, the playbook for the sky. Before anyone can start to crunch the numbers for a flight, the entire aviation world has to agree on a few fundamental rules of the game. And the most fundamental rule of all? Well, everyone has to agree on what the air actually is. I mean, the atmosphere changes wildly all over the world, right? So aviation uses a single universal model, the International Standard Atmosphere, or ISA. Think of it as a baseline, a standard day for temperature, pressure, and density that ensures a pilot in Dubai and an engineer in Denver are using the exact same math. And this playbook is a huge global effort. You've got the big international body, ICAO, which sets the broad standards. Then you have national authorities like the FAA in the US that create their own specific regulations. It's this incredible collaborative system designed to make sure a plane certified in one country is considered safe to fly absolutely anywhere in the world. Now, let's get into what is arguably the most critical phase of any flight: takeoff. We're talking about the point of no return, where years of intense calculation prepare pilots for split-second decisions. So let me ask you, what do you think is the single most critical moment of a flight? It's not turbulence, it's not even the landing. All the data is clear, it's the takeoff roll. You're at maximum power, you're at high speed, and you're just feet off the ground. Everything has to go right. And if it doesn't, you better believe there's a plan. That plan begins with something called the accelerate stop distance. It answers one simple but vital question. If an engine fails at the worst possible moment, is there enough runway left to slam on the brakes and stop safely? This number is calculated for every single takeoff without fail. And this brings us to that crucial pre-calculated speed called V1. The best way to think of it is as a literal line in the sand on the runway. Before you hit V1, any problem means you stop. But the moment you pass it, you are committed. You are going flying. The math has already made the decision. The takeoff must continue, even with an engine failure. And this right here is the absolute genius of aviation safety. Before the plane even moves an inch, the calculations have already guaranteed that the runway is long enough for both outcomes. You can abort before V1, or you can continue after it. Either way, the math has already confirmed it can be done safely. Okay, so we're airborne. Now the mission changes completely. We're navigating the thin air. The calculations shift away from raw takeoff power to things like efficiency, endurance, and of course, planning for the unexpected. When you're in cruise, the main focus shifts to efficiency. Pilots use charts just like this one to find the sweet spot, that perfect speed to fly the farthest on the least amount of fuel. But even while they're optimizing for efficiency, those safety calculations are constantly running in the background, always asking, what if? And here is a really big what if. You're cruising at 38,000 feet, but what happens if an engine fails while you're flying over a massive mountain range? You can't maintain your altitude. You have to descend. But how do you do that without hitting a mountain? The answer is a pre-planned, almost graceful maneuver called the drift down procedure. This is not some chaotic fall from the sky. It is a precise four-step process. Pilots apply max power to the working engines, they slow the aircraft down to its most efficient gliding speed, and then they follow a pre-calculated descent path that they already know is completely clear of obstacles all the way to a safe diversion airport. And how clear is that path? Well, the regulations require that the calculated flight path, which already has safety margins built right in, must clear any obstacle along that escape route by a minimum of 2,000 feet. That's not just clearing the mountains, that's soaring over them with a huge buffer of safety. From the challenges of thin air, we arrive at the final test of precision: sticking the landing. And as you'd probably expect by now, the calculations here are just as rigorous. So, how much runway does a plane need to land? Well, there's the actual distance it physically uses, and then there's the required distance. And the regulations demand that the available runway must be a staggering 1.67 times longer than what's actually needed on a dry day. That's a 67% safety margin built in before the flight even leaves the gate, just to account for any variable you could imagine. Takeoff. cruise, landing. What's the one common thread through all of this? It's this core concept, the margin of safety. Ultimately, it all comes down to this one idea. This quote says it perfectly. The entire field of aircraft performance is built on creating calculated, non-negotiable margins of safety. It's not about hoping for the best. It's about mathematically guaranteeing safety by building layers upon layers of protection into every single flight. So next time you're on a plane and you hear those engines roar to life, you'll know it's not just noise. It's the sound of physics, meticulous planning, and non-negotiable safety margins all coming together. So, what invisible calculation will you be thinking about?